one application of differentials is in the study of error. We mentioned that when we look at differentials, we're really focusing on how much our variables, both the input and the output variables, change. Now, if you think about change as being changing away from the correct value, a change could be interpreted as an error. Let's just take a look at this scenario. Harold and Maude have gone into business together. So, whatever differences they've had in the past, they are now happily working together as business partners. What they're going to do is they're going to be manufacturing coasters. Coasters are those things you put on coffee tables so that you can put a hot liquid on it and not hurt the table. I don't have any tables I care about that much, but my parents use coasters. Okay, so they're going to be trying to manufacture coasters. This is probably bigger than the actual ones will be, but they're going to try to manufacture coasters in the form of a disc. And their target is to try to have the radius be 4 centimeters. Okay. And of course, there's going to be a corresponding area associated with that. I know that the area of a disc is just pi times the radius squared. Now I can interpret that as r is my input variable and area A is my output variable. So r is in the role where x usually is, and A is in the role where y usually is. And the graph of this would look like just a portion, the right half of a parabola. Okay, now I've only drawn the right half because even Harold and Maude aren't capable of measuring a negative radius or getting a negative area. Now, if their target is that they're trying to measure the radius to be 4 centimeters, that means that they're hoping that the area will be 16 pi, and that would be square centimeters. Okay. But anytime you're measuring something, you're going to make an error. It's just going to happen. That could be your fault, and in the case of Harold and Maude, human incompetence is highly, highly probable. Okay. But also it could have something to do with the instruments you're using to measure things. They're not going to be perfect. Okay. So what we can do is we can say, I'm going to interpret delta r, and I'm going to set that equal to dr as being r minus 4, the signed distance that we are away from 4. That's going to be the error in the radius. Okay. Now, I said it's a signed distance that we are away from 4. They might measure the radius too big so that they'd have something bigger than 4, in which case delta r, which I'm going to set equal to dr, would be a positive number. If they measure the radius too small, a value to the left of 4 minus 4 would give me a negative error. So error is always a signed quantity, indicating that you can measure something too big or too small. Okay. Delta A then would be the error in the area. Okay. So if they measure the radius wrong, that's going to mean they're going to get the wrong area. Now, we are suspending our disbelief a little bit and supposing that they do manage to get something perfectly round. Okay, so that this will still hold, but just with whatever radius they've measured. Okay. But we can then say, okay, I want to know if I measure the radius wrong, how much is that going to mean that the area is off? And the area is kind of relevant because that's going to affect how much material they need to buy. Okay. All right. So, actually finding the error in the area, if, let's say they had undermeasured the radius here, I know that this would be my delta R and that would be my delta A. To actually calculate delta A, they'd have to calculate the area that they get with the wrong radius and subtract the 16 pi that they were shooting for. Okay? But we can approximate that using differentials. So on this tangent line, if we set dr equal to delta r, then we could calculate dA, and that differential will approximate the error that we would get in the area. Okay. All right, so let's just suppose that they're fairly confident that they can measure the radius accurate within, let's just say, 0.05 centimeters. Okay. Now really, the way that we ought to write that is then that the absolute value of dr would be less than or equal to 0.05. Because remember, error and differentials are signed quantities. They can be positive or negative because you can measure something too big or too small. Okay? And if you know that you can be accurate within 0.05 centimeters, that's not the same as saying I'm going to be off by exactly 0.05 centimeters. This allows for you being off by only 0.03 centimeters. Okay? So this is really what we ought to write. What the book does, and I'm not crazy about it, but I'll let you do it too, is they just say dr equals 0.05. What they're actually doing there is they're looking at the absolute value of the worst case scenario. And generally, when we're trying to approximate errors, we are looking at the worst case scenario. Okay. If I know I'm accurate within a range of this, I want to look at the extremes of that range to see, okay, if I actually do make the biggest mistake that I think is likely for me to make, can I live with the consequences? Okay. And just taking the absolute value, because we're just focusing here on the amount that we're off by. And that could be an amount that we're too high or an amount that we're too low. Okay, so I know that rise is equal to slope times run. So that's going to mean dA, because I've got A here on the vertical axis, is equal to A prime, and I'm just going to indicate that's going to be a function of r. Area is a function of radius, so its derivative will be a function of the radius, times dr. Now what I want to do is I want to evaluate dA when the radius is 4. I want to look at the tangent line at the point that I was trying to get, at the right value for the radius, and when dr is 0.05. Okay. So let's see. Oh, before I plug in, I'm going to need to calculate what A prime is, aren't I? We'll do that, shall we? Okay. So I'm going to take the derivative with respect to r. Now, this is not implicit differentiation. I'm not viewing this as a function of time. R is what I'm putting on my horizontal axis. It's in the role that x is usually in. It's my input variable. So A prime is just 2 pi r. So dA is 2 pi r dr. So now, if I plug in 4 for r and 0.05 for dr, let's see what we get. We're going to have 8 times 0.05, that's going to be 0.4 times pi. Okay. That would be square inches. So we would estimate that the worst case scenario, if we measure the radius as wrong as we're going to get it, is that the area would be off by 0.4 pi square centimeters. It's an estimate, okay, but sometimes that's good enough. If I can estimate that that's the worst case scenario and that's safely within the realm of how much material I have to work with, I'm not too concerned. Okay. Now, sometimes it can be difficult to get a sense of whether that's a big deal or not. Okay. Is that a significant amount of area or not? That's just the amount of error that we're talking about. So we can also talk in terms of percent error. So we've said dr, which is the same as delta r, is the error in the radius, and delta A is the error in the area, and we approximated that with dA. Okay. If I want to put things in perspective, I can switch to talking about percent error. So the percent error in the radius is just going to equal the amount of error in the radius divided by the target radius. So in this case, delta R, we said, was at most 0.05, and R, the R value that we were shooting for, was 4. I might almost want to call that R naught. That's the R value that we care about, that we're calculating the point of tangency at. All right, let's see, that would be multiplied by 100 over 100. That would be 5 over 400. Now that's giving me the percent error as a fraction. I can convert to a decimal and then move the decimal and get to a percent. That's going to be 1.25%. Okay. Now the percent error in the area, that would be delta A over A, where A is representing the target area. So that would be approximately dA over 16 pi, which would be 0.4 pi over 16 pi. I can cancel those pi's. I'm going to multiply by 1 in the form of 10 tenths. So that's going to give me 4 over 160, which reduces to 1 over 40. Okay. And to get that to a percent, I can just do the division and then move the decimal. So let's see, 40 doesn't go into 10, it goes into 100 twice, and into 205 times. So we get 0.025, which is of course 2.5%. Okay. So the percent error in radius is about 1.25%. The percent error in the area we can expect to be about twice as much. Kind of interesting to see.